All right, so we left off at number 17, which is the one that y'all sent in for, but since last Tuesday, and as Anna suggested, everybody did well on those. So I do we need to actually go over or just move right along to number 18? Moving along to number 18 then. We for the good news is between numbers 18 and like number 26, it's more of just repeating the things that we've already done, literally just copying and pasting code from above, making a few changes here and there. But I went ahead and in that Google Docs, which I'll resend this thing in the chat. So here's the link for the Google Docs. And I went ahead and updated that with just the code itself for 17 through 26. But so starting with number 18 here, we're wanting to do the three component PCA, but with the oblique, specifically the Obleman rotation. And so all we'll do is we'll paste in our code from before, where we did our three-factor Varimax up here on number 16. And all we're doing is
Do you want to screen share with us,
oh,
Austin?
sorry. I forget that I'm... Oh, wait. It's disabled. I need you to enable it,
Oh,
Anna.
crap. Oh, yep.
My bad.
One sec.
I knew I was forgetting something here.
I cannot remember for the life of me how I can make it screen share with other people. Let's see.
While we're trying to get the screen share working, like I was saying, everyone on just copy and paste the code from number 16 down to number 18, and all you're doing is changing the rotation from Varimax to Obleman to
Try it now, Austin.
let's see. There we go. All right. So we're creating PCA OB3. So our Obleman rotation with three components. For getting these correlations between them, as you may recall, there's if we look at PCA OB3 dollar sign, our R scores is those correlations, and we just want to round those down to 3 digits, so we'll just wrap that in round comma 3. Is the screen size here good? Can everybody see what's happening? All right. So when we look at the correlations between our three components, once again, I just want to reinforce that. Notice that it's TC1, TC3, TC2. So make sure when you're transferring that over to the homework, you're looking between the correct pairs as you go. And I oops, did not remove the answer from this particular one on the homework here. So when we look at the correlations between these, we have the correlation between TC1 and TC3 is 0.318. And oh, that should just be one component because a component correlates at over 0.3.
Well, there are two. The components are TC1 to TC3, so it is correct that it says two components correlate.
Okay,
They
fair enough.
correlate with each other.
Fair enough. The two components, not two of the correlations. But nonetheless, that tells us that the oblique rotation is more appropriate than our former orthogonal Varimax rotation. Does that make sense to everyone? Are we all tracking? For 19, looking at our communalities, that's the same thing, just extracting that from the PC3 or OB3 object. But I'm going to wrap that in sort and round, so I can round it to 3 digits and also just sort them in order to make it easy to look at, what's highest, what's lowest, etc. And so what is what variable has the highest communality?
Good, it's in the chat. Very nice.
All right, so we got DEP 104 with the highest, and our lowest is Discrim 104, exactly. How does this compare with our previous communalities? Let me scroll up and run those previous ones so we can look at it. So again, here on top, the ones we're looking at currently, and then on bottom, we have the former one. Please. Sorry, I think I ran the wrong one.
Well, in this case, they are identical because in each of these two, we extracted 3 components.
Yeah, I meant to.
Is that what?
I meant to run the 4.
Okay. Casey, sorry for the confusion. We are trying to compare what happens when you extract more components or fewer components. So, but last time we started talking about the communalities as representing what? Morgan's right. If we extract more information, then we're going to have higher communalities overall. So, for example, what happened, our highest communality when we extracted 3 components was DEP 104 with a value of 0.683. But when we extracted 4, what happened to DEP 104? Yeah, it went up. We got from 0.683 to 0.699. And the last, when we took out 3, we had one variable that you all wrote about in number 17 that didn't load on anything, and it had the smallest communality by far, Discrim 104, which had 0.09. But when we ran it with 4 components extracted, what happened to Discrim 104's communality? Yeah, it also went up. And it went up quite a bit. And if you remember from when we looked at that prior one where we extracted 4 components, it wasn't an outlier variable. It actually had found a home. Whereas when we took out 3, Discrim 104 didn't belong on any of the components. It was like, I'm an outsider, I'm an outcast, I'm an outlier. So it's just another example of how the greater number of things you extract, the more you explain, but also the less parsimonious it is.
Any other questions? On number 19, there's another typo where it says IE 3. That was just a vestige of copying and pasting questions, I believe, because if we recall, when we look at our 50% variance explained as far as how to different ways to look at how many components we should use, that 50% variance explained was it gave us 5 components. We need 5 components to explain 50% of the variance. So here on number 19, that should be conduct a PCA based on explaining over 50% of the variance using Varimax rotation, which means we want to extract 5 components here. And so again, just changing a little bit of the previous one, that we're changing it to, we want that Varimax rotation, and we're going to change n factors to 5 to tell it we want 5 components. And we'll call this one PCA Vmax 5. And then first thing that we want to do is examine those communalities.
Yeah, so this is interesting. Look at what happened to Discrim 104 in this case.
Let me pull up the old one too. So we're on the old one first. And now
so this is when we had a 3. Yeah, Casey and Isabel are like, whoa. It went from 0.09 and being an outlier to suddenly being the highest. So what do you think might have happened? And it's the highest by a lot. It's like 84% of its variance is now in this model with 5 components. What do you think happened to Discrim? It had been an outlier. Now what happened? Yes, Casey, she's on it, man. Everybody should podcast and walk in the morning. It is basically found it's basically like, fine, you guys don't want me in your component, I'll go build my own component. And so it made its 5th component, and it said, I belong here. Becca's got it too.
So I presume we don't need to walk through piece by piece of these other 3 in number 19, because all it's asking is the highest, lowest, and what we just discussed, which is how those compare with the previous. So then for on number 20, our rotated component matrix, once again, we're just going to use print psych, set our cut to 0.32. That way we can look for complex loadings and such. So how many of this 5 component Varimax rotated thing, how many of these have complex loadings?
Yeah.
Yep.
Good. Everyone's seeing the 3.
Getting those 3s rolling in. And just a reminder, that's, any of them that load greater than 0.32 on 2 or more components. Are there any variables that don't load on any components at all? Got a bunch of no's rolling in, which is correct. Looking at what variable loads highest on RC1?
Good. SC102.
Yep. Then RC3.
we're seeing a pattern. We keep getting these same variables as the highest loading ones, step 104.
Yep. And so then for that one, we would continue to roll on through each of the 5 components. Simple enough. What about the marker variables? Can someone remind us what we're looking for in the marker variables? Above 0.6. And if you wanted to have an easy way of looking at that, just as a reminder, you can just change your cut point to 0.6. And now we can see how many marker variables are there in RC1.
Good. So I wanted to pause for a moment here. This is excellent. And you realize that we keep doing the same thing over and over again, right? We keep trying another PCA with a different number of components, or an oblique versus an orthogonal rotation. We keep looking at complex loadings. We keep looking at marker variables. And that's because we want to get to this point where we can say, okay, what is the least number of components I can extract that retains the most amount of information, where each component actually means. And right now we have a component 5, that is problematic. It is where our outlier variable found its home, but nowhere else, no other variable has found a home with it. So it's really kind of a solitary, we had one other buddy, but it was complexly loaded, and it's really a standalone. And so that's not a component, that's still just a variable, which means this is what it looks like when you over extract components in a PCA or an EFA. You really want to have each component have a good few 2 to 3 to 4 marker variables. And if you have fewer than 2 or 3, then you have an ill-defined component, and you might as well toss it out, because that's no better than a single variable. That's kind of where there's no p-value for this, but we do want to just use some rules and some logic to try to decide if we're under extracting, we're properly extracting, or we're over extracting. This is a clear example of over extraction.
Yeah, and so then on the next part of the problem, here on E, where it asks if any seem unstable or ill-defined, that's exactly what it's talking about. So that component number 5, as she was saying, only has that one marker variable and nothing else that really loads on it. So that's a rather ill-defined component. Getting down to F, where we'd want to name each component. Let me pull our data dictionary back up. Sorry, I knew I was forgetting to pull something up. Our code book. Alright, so with looking at this first component, all of our SEs, what might you name the component number 1? Noah says positive self-worth. That could work. Positive self-esteem, sure.
His self-esteem is worth fine too,
yeah. And then what about component number 4 then? Worthlessness, that works. Inefficacy, sure, I'd buy that. Component 3 seems pretty straightforward. It's all of our depression items, so calling that depression is fine. And then you've got component number 5 out there. What might we call component 5? Not everyone all at once.
Jake finally threw his hat in the ring.
No.
Yeah, can you pull up the data dictionary to all the discrimination items for a moment?
Is it not showing?
Yeah, but I want 101 as well.
Oh.
Good. Okay, I want you guys to notice something about discrimination. These are good names: economic discrimination, non-discrimination, something like that. Discrimination 101, 2, 3, and 5 are worded in a particular way that's different from 104. What's different about 104? Yeah, Nia's got it. It's basically, it's not stating in agreement with 104 doesn't mean you agree that there's discrimination. Agreement with 104 actually means that you agree that there's equality, right? And so that is a reverse coded item. That's why there's a Y there in column B. And it's interesting that the reverse coded item didn't really go with the forward coded items, right? Can we look at self-esteem as well? Let's look at the 10 self-esteem items. You've missed one. There we go. Okay. So what are the self-esteem items that are reverse coded? Yeah, notice that the reverse coded items either load complexly or they tend to find their own component. This is like the bane of the existence, like of psychometric existence. When you're trying to create a scale, you're told you want to create some reverse coded items because it's important to make sure people don't break set, or they break set, that they're not always just saying yes, 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 that they're actually reading. So that's why it's oftentimes the case that we want to create reverse coded items, basically to make sure people are paying attention. But the problem with reverse coded items is that it's conceptually not the same thing, for example, to agree that I am worthless than to disagree that I have worth. Even though we write them as though they're the same thing, it's not actually the same. So saying I love stats is not the same thing as saying I don't hate stats, right? And what happens then is that the distribution of responses for reverse coded items tends to look different than the distribution of responses for forward coded items. And when you do a PCA or an EFA, you are often going to find that your reverse coded items don't quite go all together with your forward coded items, and they kind of tend to break off into this other component. But that's because there's a methodological explanation that agreeing with something is not the same as disagreeing with its opposite. So you'll notice that not just here in our homework, but you're going to notice that in any EFA paper you pick up or whatever, that there tends to be that, or if you do a CFA, there tends to be this methodological piece that is going to be partly driving your correlations among your variables.
All right. Anything other questions before we move on? So, cruising into number 21, basically what we want to do.
Hold on, there's a question. there's a question, sorry. Morgan asked, first of all, why do we reverse code? And the answer is because that's good scale development, is to make sure that you're making it's almost like an attention check on people to make sure that they don't just start like check all the way down. How do you know if you keep them in the scale? Well, in this case, we might in fact model self-esteem as containing both feelings of self-worth and relatedly but distinct feelings of worthlessness. So we might in fact keep them both in there under a higher order factor of self-esteem, but then consider that self-esteem has these kind of two pieces, right? I'm a person of worth versus I don't think I'm worthless. So that's sometimes what we will do. Sometimes people, like in discrimination, where discrim 104, the reverse coded items, yes, like subscales, where reverse coded items kind of didn't, there was only one, so it ended up being an outlier. We might probably delete that one item because it doesn't have a family to go with to make its own component. And then you'll see a lot of people write scales that have great psychometric properties, but they actually contain no reverse coded items, and that's probably on purpose.
Then another thing to keep in mind, Morgan, when you're checking like your alphas, your reliabilities for those using the alpha function from the PSYC package, it also gives you like the item total correlations and like the reliability if removed analysis. So if you're looking and your reliability is garbage, your reliability is say 0.6 or 0.5 whatever, and then you look in just this one Discrim 104 item, it says that if you remove that item that your reliability is up at 0.86 or whatever, then you have a good argument for saying we need to take this item out. It doesn't hang with the rest. But yeah, so then on number 21, we're wanting to take out, we're going to take out SE 103, SE 105, and Discrim 104. These are the three items that were causing us some problems and complexly loading on several of our different rotations and such. So here I'm just going to subset and make PCA DF2 by taking those three out. And so looking at our KMO that Kaiser, help me out here, Anna.
Meyer-Olkin.
There we go. Remember, this is just a single function from the PSYC package, KMO. And so when we run KMO on our new subset PCA DF that doesn't have those three variables, we're looking here. 0.82 is our KMO score. Back up, compare that with our initial KMO.
Do you guys remember what is the KMO value that we're looking for to decide if the data are factorable? Yeah, Noah's right. We're looking for a value of KMO above 0.6.
So looking at our KMO, it's gone down just a little bit, but not concerningly. And so then for our Bartlett test of sphericity, Again, this is just the Bartlett.test function from the psych package, and we're going to put in our PCA DF2 and P is less than 0.001.
So the key here is that every time we didn't have to keep testing KMO and Bartlett as long as we were working with the same 19 variables. So 19 variables with 3 components, 4 components, 5 components, orthogonal, oblique rotation, that's all fine. But in this case, across many of our analyses, we kept finding 2 of our self-esteem variables and 1 of our discrimination variables were problematic. So we decided, let's take those out. Let's keep the 16 other ones in, and let's now start over. But because we're starting now from a new set of variables, they weren't the original 19, they're now 16 of them. We have to go back and redo all of our assumption checking that has to do with the factorability of the data. We already know like the individual correlations are fine, the distributions are fine, linearity, all that's fine. But the issues we have to deal with now are about factorability of the data because we don't have the same data set. We have a reduced data set. So when you remove items or when you add items to a PCA, you got to go back to this step.
And then here, what we're wanting to redo our 4-component Obleman PCA, but with our new data set. So I'm just going to call this one PCA.ob4.update. And here it would be the same as our first PCA4 or PCA OB4, only we're changing from PCA DF to PCA DF2. And now to get those communalities, again, we just call those communalities. And I'm going to wrap it in round and sort for us. As far as naming the biggest and smallest, that's simple and straightforward enough. How does this compare, though, to the first PCA that we did?
So it was also oblique, it was also 4, but it was with 19 variables.
So here at the top we've got our updated one, and down on the bottom this is the first PCA that we ran.
Yeah, people are noticing that there are a little bit higher communalities overall, and that's because the data set itself now contains items that actually go more with each other. It doesn't have as many of the items that are like have a little bit less in common with the whole data set. So originally when we had Discrim 104, it really made it so that all the variables had a little bit less in common with each other because Discrim 104 was part of the game. And now all the communalities have increased a little bit because they really do have more in common with each other, and that's going to be reflected in the extraction of components and the explained variance from the extracted components.
There we go. Sorry, I was having some technical difficulties. My mouse cursor decided to disappear. All right. So Moving along into number 23, looking at, this says the total variance.
Sorry, Jake had a notation that in B and D in our item 22 were the same question. So is that true in the homework or in the R script?
Probably in the R script. Just ignore it. Let's see, 22. Nope, it is in the homework. It just repeats it twice.
Let me see if I can figure that out real quick.
It's comparing the smallest. How does that compare? And then the biggest, and how does that compare?
The largest communality relative to the first PCA, and then the smallest communality relative to the first PCA. Sorry, that's why they sound like the same question, but they were referring to different parts.
And then on number 23, it's where it says examine the total variance explained table. That's not verbiage we're used to. That's what SPSS calls it. We just want to examine the eigenvalues, and we want to look at those eigenvalues for PCA OB for update $values. That will give us those eigenvalues, and if we want to round those, let's say round that to 3, and we can see those individual eigenvalues.
And so, of course, we didn't extract all 16. So when the next item asks about what are the eigenvalues for each extracted component, make sure that you only report the eigenvalues for the first 4 components.
How much variance in the original variables is each component accounting for? Whenever we've been running PSYC, we've been mostly focusing on these actual loadings up here, but down here below it is where we're looking at proportions of variance explained by each one. So TC1, it's You'll notice that the proportion and cumulative variance, again, this should just be a refresher because we kind of touched on this last Tuesday, or maybe it was before spring break, but we're looking at, it gives us the individual amount of variance explained and then that cumulative proportion of variance explained for each one.
So I'm putting in the chat how component 1 here in this Varimax rotation explains 15.4% of the variance in the X variables. And I said 2, but I actually meant 3, I'm sorry. Component 3 explains 14.5% of the variance. And if you add those 2 together, you end up that you're explaining a total of 29.8% of the variance in the variables. But that is only true if you do an orthogonal rotation where there is no overlap. The percentages, the cumulative percent variance is simply additive only if you're doing Varimax or an orthogonal rotation. Once we do this again in an oblique rotation, or if we were to do this again in an oblique rotation, I can't remember if we're going to, Yes, I think we're doing it next. That you'll see that the cumulative variance is no longer simply additive.
Yeah. And then for the total variance, how much of the total variance in the original variables is accounted for?
So how much of the variance in the original x variables do our four components explain? Did we run an oblique? So Jake is right. We said 53.6%. Noah's got it too. Is this an oblique rotation that you just ran?
This one is, yes, the Oppelman.
Okay, so then it is a strange thing. It shouldn't have been proportion, shouldn't have been exactly additive. Stephanie's asking, where is the 53.6 coming from? Can you highlight and show or explain?
For this one, well, and that Anna, it may be right here is where might be what you're talking about, the proportion explained, cumulative proportion, because these are 28.7 and 26.9, or is that
It's still 55.6.
yeah, and that is strange, although
well, you know what it could be? These could be partials. These could be partialing out for the overlap.
yeah, and the is the set of components.
Okay, so there's a question about why it shouldn't be additive for the oblique, and so let me try to explain that a little bit. I'm gonna take control again and share for a moment, if that's okay.
Mm-hmm.
Okay, so give me just a moment. Okay. So we have a component, which you can think of almost like an x variable, a component. And the component has its variables that load on it. So like x1 and x2 and, say x4, okay? And so if let's say for a moment that x1 doesn't overlap with anybody else, right? So it just loads on component 1. So it's got all of this overlap between itself and its component is what we call our communality, or our h squared. Now, if we have an oblique rotation, this is fine. In an orthogonal rotation, our component 2 is over here. And here we have some overlap with x3 and some other overlap with x6. But remember that every x variable belongs to only one component. And these two components don't overlap with each other at all, right? So the correlation is 0 because we forced it to be that way by a orthogonal rotation. So whatever variance is over here for the x variable is only going to be over here, and it's not going to have any overlap with any other component. That means that if you were to add all of the variance explained in x1 plus x2 plus x3, whatever, you basically can simply add. So component 1 explains all of this variance in the x variables. That's the total amount of variance in component 1 that's explained. Component 2 explains all of this variance in the original x variables, right? And you can see clearly they don't overlap. So you should be able to add this to this and get a total variance in the original x variables explained by your two components, the ones that were unassociated with each other. But if you have an oblique rotation, that's the equivalent of having two components that not only share things with their x variables, but also share things with each other right here. And that's the problem with trying to just add a variance explained, is because the C1 might explain this variance in these x variables, but C1 and C2 are also correlated with each other. And so what I think is happening is that the output in R is giving you what's called a partial correlation. So it's the correlation, right, between x, say all the x variables and component 1, but partialing out the correlation between C1 and C2. And that's why it's acting cumulatively. I'm pretty sure that's what's happening. But that's why it shouldn't be additive. I don't know if the x variables don't, because the components are also to some extent correlated with each other. Okay, I'm going to turn it back over to you, Austin, make you the host again, so you can keep screen sharing. Okay, cool.
All right, and then on this next one on C, where it's asking about the extracted variance, is that, I can't tell from the wording, is that going back to the answer here should be 100% because it's a PCA and not a factor analysis?
Number C, how much total variance in the original variables is the set of components extracted for account for? How much of the total variance in the original variables is the set of components extracted accounting for? I probably should say accounting for. So no, it's the total variance.
Okay.
In the extracted four components, which is, I think, that 53.6%.
There. And just keep in mind, the reason that these are out of that order is because it will put the components in order, descending order of explained variance. So that's why TC2 is out here at last, because TC1 examines 15.4%, TC3 is 14.5, TC4 is 13.1, TC2 is 10.7, to total 53.6%. So then when we get into number 24, it's running off this exact same thing that we just now ran. It's telling you to examine the pattern matrix. That's asking you to look at this loadings table here. How many complexly loaded variables do we have now with our updated 4-factor Oblman rotated PCA? Why did I lose my chat? There we go.
Yeah, we're super happy. This is like, I look at this pattern matrix and I think it's a beautiful work of art. None of the variables are complexly loaded. I think it's just gorgeous.
And so then, as far as how that compares, obviously in our previous ones we did have complexly loaded variables. That's no longer the case. Not gonna kill time looking at the highest loadings variables for each component. For marker variables, if we want to check that out, So looking at it now, how many marker variables do we have for each component? Or asked another way, are there any components that seem ill-defined? Nope.
Yeah, ill-defined meant what again, guys? Right, just like one marker variable. And in all these cases, we have 2, 3, or 4. So pretty well defined, especially given the small number of items per component.
And then as far as naming them, again, like that'll be on you. You can figure that out. For number 25, looking at that component correlation matrix, it's down here, same function that we had ran before. And looking at our correlations down here, what can you say about the type of rotations that we should be using?
So to determine if our orthogonal or oblique, we would need to have all of the correlations below 0.3 or 0.32. Morgan's saying she's struggling with keeping up with her screen, so she's a little bit lost. Okay, thank you, Morgan. That's cool. Right now, we're looking at the component correlations. So we ran our 4-component with an oblique rotation with 16 variables. And where are people lost? Did we have a chance to look at marker variables okay? Did everybody see that part okay? I'm just trying to get a sense of where people got lost.
On number 23, Casey, how we should report what we had, and like this is all you'll need in the R code is extracting those the 4 eigenvalues from your using the $values, that is the eigenvalues.
Right, I think we just need to look at the output again. Thank you.
So here's the eigenvalue for the first, here's the eigenvalue for the second component, here's the eigenvalue for the third, and here's the eigenvalue for the fourth. So all you'll need to do is report those first 4 eigenvalues, since we only extracted those 4 components.
I think it's probably here on B and C that are most confusing. But let's, for a moment, make sure everybody's able to run that. So Rosalie asked why we report only the first 4. It's a great question. We have up through 16 there, which would be the eigenvalues for every single component. But we're only going to report the first 4 because those are the only 4 that we actually extracted in this analysis for interpretation. We basically had run our parallel analysis. We actually probably should have rerun the parallel analysis with only these 16 variables because our parallel analysis was run with 19. But spoiler alert, it still would have said 4. And so with our parallel analysis, we only took 4, which is why I only need you to report the first 4 eigenvalues. Okay, so are we caught up to this point? Sort of caught up, or at least kind of like I know how to work things up through this point? Because the next one I think is the little bit tougher, the one which is now reporting about variance and cumulative variance. Okay, can you read part, Austin, where we look at that table again, the one that was causing us confusion?
It's this one.
Okay, yeah. So we have there sum of squares loading. We have the proportion of variance. We have cumulative variance. We have proportion explained and cumulative proportion. Okay. Ignore the sum of square loadings, the first line. Ignore the proportion explained, the next to last line, and the cumulative proportion, last line. And look only at the lines that say proportion bar and cumulative bar. So the proportion bar is the proportion of variance in the x variables that is explained by that component. So component 1 explains 15.4% of the variance in the x variables. Does everybody see where that number comes from? Okay. And of course, when you're talking about just the first component, the proportion of variance in the x variables explained by the first component is the same as the total amount of variance explained by one component. Okay. Then we extracted the next one, which is labeled TC3. By itself, TC3 explained 14.5% of the variance in the x variables. But once you consider the combination of TC1 and TC3 together, those two components explain 29.8% of the variance in the x variables. So can someone tell me what is the unique variance in the x variables that TC4 explains? Good, 13.1%. And if you take together TC1, TC3, and TC4, how much total variance in the x variables are those 3 explaining? 43%. Excellent. So all we're asking here is what's the unique variance in the x variable each component is explaining, and in total, these 4 components, how much variance in the original x variables do they explain? So how much variance do they all explain? Good. 53.6. Excellent. And if you remember, 100%, you're welcome. 100% of the variance is what got originally thrown into the model. And we're getting back over half of it with just 4 components. So that's considered good. In fact, one of the criteria for some of the extraction dumbass rules is more than 50% of the variance. So together, these components explain 53.6% of the variance in the original x variables, and that table tells you where. So we'll just hone in on those 2 lines in that table.
Yeah, and I'm going to
Thank you guys for letting us know when you're pausing, because it's really, we don't know how to judge that. So it's really helpful to have you chat in and interrupt.
Yeah. And I want to pull back up this screenshot that we talked about last week before, I suppose. with this is what the communalities table output looks like on SPSS. And as Anna just now said, remembering that initially it's 100% of the variance that goes into it, and that's why in this initial column, we have all ones, whereas this extraction column is what, if we run our communalities, these extraction column is the values that we get. It doesn't show this initial column just because it's all it's all ones, it's all 100%. That will change, however, here on our next problem when we get into getting into the factor analysis. So we'll come back and revisit this here in just a second.
Wait, there's a quick question by Stephanie. So the extraction column is the proportion of variance row?
No, the extraction column is the communalities. When we run communalities, and for this specific example, this is just the communalities. If we go back up to the first PCA that we did and look at our communalities up here, PCA OB4, if we compare that to this one, Discrim 101 is 0.527. We see that down here. Discrim 102, 0.271. So these communalities, what SPSS calls extraction is just what R calls the communalities. And then go back up so we can keep an eye on our correlations here. And so what we've done all of the PCAs that we're going to do for this lesson, and instead we're going to switch to conducting a factor analysis. But given what we've done so far, which PCA best represents our data?
We have a couple of options. One is an orthogonal one with 16 variables. One is an oblique one with 16 variables. Can we look at this component correlation that is up on the screen share right now? Because I think we were talking about this, but then we paused and went backwards. So this tells us, we ran it as an oblique rotation. We haven't run the orthogonal yet with 16 variables. And we always start with oblique so that we can look at the correlations among our components, decide if orthogonal is even feasible, or if to do an orthogonal rotation would be to distort reality too much. And distorting reality too much is defined as forcing correlations among the components to be zero when in fact they are correlated or they overlap about 10% or more. And so depending on who you read, you might see that if a correlation between a component is above 0.3 or above 0.32, these are just a couple of the guidelines, you should not do an orthogonal rotation. You're forcing something to be uncorrelated that actually is correlated in real life. So based on the component correlations we see on the screen right now, are we allowed to move forward with making an orthogonal rotation? Good. Yeah, we're not allowed. So we're not even going to run it because we have at least one correlation above 0.32 and a couple that are above 0.3. So we're leaving it at oblique rotation with 16 variables for this analysis.
And with our 4 components, or in this case now we're going to be switching it to factor analysis. So we're going to leave it with 4 factors instead. So we'll go ahead and conduct this. So This is similar to the arguments that you use for the principal components, only now FA is what is going to be the function that we use. Again, this is from the PSYC package. Since we decided that the one with those 3 variables removed is better, we'll tell it to do a factor analysis with PCA DF2. Our number of factors will be 4. N factors equals 4. Rotate, we decided Obleman was our best rotation. There's one additional argument that we have to include with factor analyses, and that is FM. And this is the factoring method. Because in the problem it tells us that we want to use principal access factoring, the FM will equal, in quotes, PA. If you look in the help file for the FA function, it'll tell you that FM equals min res does minimum residuals. There's ULS. There's a bunch of different things. So all you need to know for now is that we want to do principal axis factoring. So we're going to say FM equals PA, and then we also need to normalize to do the Kaiser normalization. We're going to store that. I'm just going to call it FA4. Now, here, as y'all are getting all that taken care of, what I'm about to show you, I want to be clear from the beginning that this is not something that you necessarily need to worry about remembering. Basically, none of these functions have a way to pull up that this table that we've been looking at with this initial column. So I'm going to show you a roundabout way that we're going to create this column, but this is not something that you'll necessarily need to be replicating. So I'm going to go ahead and copy over. Well, I'll just put it in the chat, I suppose. So without explaining what this code does, just trust me when I say that if you run these 3 lines of code, it will create something called H2 initial. And I'm going to bind that with FA4 $ communality, which again, this does the same thing as before, where that gives us those extracted communalities. And so if we were to run this in SPSS, this is what that table would look like. So again, this specific table is not from this factor analysis, but this initial column over here would have these values right here in it, and then this second column over here would be our extracted column. So the important thing to keep in mind here is more of a conceptual understanding of this. Is one of the big differences between PCA and factor analysis, is that in this factor analysis, we're no longer including 100% of that variance in that initial thing, but now rather we are looking at a smaller portion of the variance. And Anna, I'll let you.
So in our SPSS table, the white ones labeled communalities that we see on the screen, it's letting us know right away it's a PCA, because in PCA we examine both overlap and unique variance. We throw it all into our model. So that's why the initial variance is always 1, because it's 100%. But in EFA, you don't put in all of the initial variance. You only throw in what it already has in common or overlaps with all the other X variables. So for example, in Discrim 101, our initial communality is 0.179. And that's because discrimination overlaps with all the other 15 variables, such that 17.9% of its variance is overlapping. Okay. And then the second number there, 3.325, means that of the amount that it threw into the model, which was almost 18% of its variance, it got back 33% of its 18% from the extracted components. So the larger the communality initially, the more that X variable overlaps with other variables that are in the analysis. In this case, for example, depression 104 has over half of its variance overlapping with the other variables that are in the analysis. Whereas Discrim 102 has less than 10%, only 7.5% of its total variance that overlaps with the other 15 variables. So it's just another way of reminding you that factor analysis doesn't analyze all of the variance in the X variables. It only analyzes shared variance, and that's what it puts into the model.
Any questions on that part so far?
And I'm gonna want to pause us here because we have 2 more minutes left, but I'm wanting to be mindful of a couple of things. So I would really like this assignment to be turned in next Thursday, which means we're gonna pause here for the purposes of your homework. And I'm going to want you to write up, do the concluding questions. So you can stop here in terms of what you answer in your homework assignment. Do the concluding questions, number 33 and 34, 35 and 36. But then on Tuesday, we are going to come back and rerun or run this factor analysis and finish the interpretation. You just don't have to turn it in your homework. But I want you to get started on the homework so that they'll be due next Thursday. The homework's basically going to cover all of the PCAs that we did. And so it's going to stop at, let's see, through number 26, skip 27 through 32, and then we'll pick up on 33. So homework is 1 through 26, 33 through 36. But we will do lab together next Tuesday so that we finish running the EFA. We talk about calculating Cronbach alphas, like the whole bit, okay?
Any last questions?
Awesome. Okay, so we'll make a note of that on Blackboard too, as kind of a reminder that you upload the homework and that it has to have those items answered. You can still keep filling in your homework for your own purposes to learn and to know how to do it on your end. Okay. Thank you, everyone.